Title of the module, Equivalence Relation. In this session, we are going to learn about relations. We define when a relation is reflexive, symmetric and transitive. And then we will move on to define equivalence relations, and we shall see some examples in this context. Some key results associated to these topics are covered in the main part of the session. A set is a well-defined collection of objects. By well-defined, we mean that any given object must either be an element of the set or not an element of the set. Collection of all vowels in the English alphabet and the collection of all real numbers, etc., are examples of sets, whereas collection of all popular people in the world, the collection of best cricketers in the world and the collection of some months in a year are not sets, as they are not examples of sets because they are not well defined. Before moving on to the definition of a relation, we shall first see what we mean by the Cartesian product of sets. A Cartesian product. If A and B are sets, then the Cartesian product of A and B is a set A cross B is equal to the set of all ordered pairs A comma B such that A belongs to A and B belongs to the set B. The definition of a relation. Let A and B denote sets. A relation from A to B is a subset of A cross B. A relation on A is a subset of A cross A. Now let us see some examples of relations. Example 1. The parent-child relation is a relation on the set of people. For example, John Jr. For example, is an element of the parent-child relation if John is the father of John Jr. Example 2. If A is equal to 1, 2, 3 and B is equal to 4 and 5, then the ordered pairs 1, 4, 2, 5 and 3, 5 is a relation from A to B. There are various types of relations like reflexive, symmetric, antisymmetric, transitive and equivalence. We shall see in detail what these are: reflexive, symmetric, transitive and the equivalence relations. We shall begin with the reflexive relation. A relation R on a set A is reflexive if and only if A, A belongs to R for all A belongs to A. Example, a relation R on the set A by the ordered pair A, B belongs to R if A minus B is divisible by 5 for A, B belongs to A is a reflexive relation on the set A since A, belongs to R for each A belongs to R. This is so because A minus A is 0 and 0 is divisible by 5, thus satisfying the condition of the relation. Now we shall elaborate what we mean by symmetric relations. A relation R on a set A is symmetric if and only if A and B belongs to A and the ordered pair A, B belongs to R implies the ordered pair B, A belongs to R. Example, a very evident example is equal to relation defined on a set A as if an element A is equal to B, then B is equal to A. That is, the ordered pair A, B belongs to R implies A is equal to B, which implies B is equal to A, which implies the ordered pair B, A belongs to R for all A, B belongs to A. Example 2. Let A be the set 1, 2, 3. Let relation R on a set A be R is equal to the set of ordered pairs 1, 2 and 2, 1 and let R dash B the set of ordered pairs 1, 2, 3, 1 and 2, 1. Here clearly R is symmetric, but R dash is not symmetric, since 1, 3 does not belong to R. Next we shall see what is an antisymmetric relation. A relation R on a set A is antisymmetric if and only if A, B belongs to A and both A, B belongs to R and B, A are also in R, then A is equal to B. Example, if S is a set and A is equal to power set of S is the power set of S, that is the set of all subsets of S. So, we denote it by P of S. Then R is equal to the set of all x, y, the ordered pair x, y such that x and y belongs to the power set of S and x is a subset of y is antisymmetric, since x is a subset of y and y is a subset of x, implies x is equal to y. We shall now move on to transitive relations. Let A be any set. A relation R on A is said to be transitive relation if and only if the ordered pair A belongs to R and the ordered pair B, C belongs to R, implies the ordered pair A, C belongs to R for all A, B and C belonging to A. That is, A is related to B and B is related to C, implies A is related to C for all A, B, C belonging to A. Example, the relation is a subset of is a transitive relation defined on a power set of sets. If A is a subset of B and B is a subset of C, then A is also a subset of C. Let A be defined as a set of elements 1, 2, 3 and 4. Consider the relation R on set A to be defined as the set of all ordered pairs 1, 1, 1, 2, 2, 1, 4, 3, 2, 2, 3, 2, 4, 2, 4, 1 and 3, 1. Then R is a transitive relation. Equivalence relations are often used to group together objects that are similar or equivalent. A relation on a set A is said to be an equivalence relation if and only if it is reflexive, symmetric and transitive, and we denote A tilde B and we say A is equivalent to B. Example, suppose A is a set of all people in the world and R be the set of all ordered pairs A, B belonging to A cross A such that A and B have the same parents. This relation is reflexive since every person has the same set of parents as himself or herself, symmetric. Since if A and B have the same parents, then so do B and A. And transitive, if A and B have the same parents and B and C have the same parents, then A and C also have the same parents. So, R is an equivalence relation. Another example, the relation is equal to is an equivalence relation on any set of numbers A as for all elements A, B, C belonging to A. We have element A is equal to A, which implies set A is reflexive. Now, element A is equal to B implies element B is equal to A, implies A is symmetric, and element A equals B and B equals C implies element A is equal to C, asserts that A is transitive. This implies that equal to as a relation is reflexive, symmetric and transitive and thus is an equivalence relation. Another example, consider a relation R on the set of integers as the set of ordered pairs A, B belonging to R if and only if A is greater than or equal to B. we need to check for the three conditions, namely reflexivity, symmetricity and transitivity. Reflexivity is as every integer is equal to itself, that is a is equal to a for all a belonging to z, it satisfies a greater than or equal to a for all a belongs to z. This implies the ordered pair a comma a belongs to R for all a belonging to z. Hence, R is reflexive. Symmetricity. For a comma b belonging to z, let the ordered pair a comma b belong to R implies a is greater than or equal to b. This does not imply that b is greater than or equal to a. For example, 12 is greater than or equal to 9, but 9 is definitely not greater than or equal to 12. Thus, R is not symmetric. Here we need not check for transitivity, as R is not symmetric immediately implies that R is not an equivalence relation. Now, we are in a position to define equivalence classes. The groups into which an equivalence relation divides the underlying set are called as equivalence classes. The equivalence class of an element is a collection of all things related to it. The equivalence classes. The equivalence class of an element A belonging to A is the set A is equal to the set of all x belongs to A such that x tilde A. Equivalence class of an element A is denoted by A bar. The set of all equivalence classes is called the quotient set of A mod tilde and is denoted by A bar tilde. A well-known sample equivalence relation is the congruence modulo n. Example, two integers a and b are equivalent if they have the same remainder after dividing by n. Consider for instance the relation of congruence modulo 3 on the set of integers z. Let R be equal to the set of all ordered pairs a comma b such that A is congruent to B mod 3. The possible remainders for n is equal to 3 are 0, 1 and 2. An equivalence class consists of those integers that have the same remainder. Hence, there are three equivalence classes in this case. The 0 bar is equal to the set of all terms minus 9, minus 6, minus 3, so on, 0, 3, 6, 9, etc. up to infinity, namely the multiples of 3 leaving no remainders. Now 1 bar is the set of all elements negative infinity all the way up to minus 8, minus 5, minus 2, 1, 4, 7, 10, etc. which are numbers which when divided by 3 yield a remainder of 1, and 2 bar is the set of all numbers negative infinity all the way up to minus 7, minus 4, minus 1, 2, 5, 8, 11, etc. which are the terms that yield the remainder 2 on dividing by 3. Similarly, one can show that the relation of congruence modulo n has n equivalence classes 0 bar, 1 bar, 2 bar, so on up to n minus 1 bar. We shall see a proposition now. Let tilde denote an equivalence relation on a set A. Consider A belonging to A, then for any x belonging to A, x tilde A if and only if x bar is equal to A bar. First, let us suppose that x bar is equal to A bar. It is evident that x belongs to x bar since x tilde x, and so x belongs to A bar, thus x tilde A. Now we suppose that x tilde A, we need to prove that x bar is equal to A bar. We prove this by proving that each of these are subsets of each other. Let x belongs to A bar, then x tilde A by definition of equivalence class. Now we have x tilde A and A tilde B, and thus x tilde B by transitivity since tilde is an equivalence relation. Since x tilde B and x belongs to B bar by definition of equivalence classes, we have shown if x belongs to A bar and then x belongs to B bar, and thus A bar is a subset of B bar by definition of a subset. Next, we will show that B bar is a subset of A bar. Let x belong to B bar, then x tilde B by definition of the equivalence class. Since A tilde B, we also have B tilde A by symmetry. Now we have x tilde B and B tilde A, and thus x tilde A by transitivity. Since x tilde A, x belongs to A bar by definition of equivalence classes. We have shown that if x belongs to B bar, then x belongs to A bar, thus B bar is a subset of A bar by definition of a subset. Therefore, x bar is equal to A bar by the definition of set equality. The next proposition, suppose tilde denotes an equivalence relation on a set A and the elements A comma B belong to A. Then A bar not equal to B bar if and only if A bar intersection B bar is equal to empty set. Proof. First, let us suppose that A bar is not equal to B bar. We must prove that the equivalence class A bar intersection B bar is equal to empty. Here we assume the contradiction, that is, suppose A bar intersection B bar is not empty, then there exists an element x belonging to A bar intersection B bar. Since x belongs to A bar, x bar is equal to A bar by the previous proposition. Similarly, since x belongs to B bar, we also have x bar is equal to B bar, and thus A bar is equal to B bar, which is a contradiction. Thus, we can conclude that A bar intersection B bar is empty. On the other hand, if A bar intersection AB bar is equal to empty, then A belongs to A bar, but A does not belong to B bar, which implies that A bar is not equal to B bar, which completes our proof. Next, we introduce an important topic of this section, namely partitions. What are partitions? A partition of a set A is a collection of disjoint, non-empty subsets of A whose union is A. These disjoint sets are called cells or blocks. The cells are set to partition A. Example, a deck of playing cards is partitioned into 4 suits, namely spades, clubs, hearts and diamonds. Example 2, consider the set S is equal to A, B, C and D. Now, the set containing the subsets A comma B, the subset C, the subset D is a partition on S. Example 3, if A is equal to the set A, B, C, D, E, F and X, then the set containing the subset A, B, F, the subset C, E, the subset D and the subset X is a partition of A. So is the subset containing the set A comma D, the set B, X, E, C and also the set F. Theorem. The equivalence classes associated with an equivalence relation on a set A form a partition of A. Also note that the converse of the above theorem is also true. That is, any partition of a set can induce an equivalence relation with the corresponding partitions as equivalence classes. Generally, a function is defined as a rule which associates to each element of a set A an element of another set B. The essential characteristic of a function is that the value which it associates with a given element is uniquely determined by that element. A function from a set A to a set B is a relation f from A to B with the property that for every A belonging to A, there is exactly one B belonging to B such that the ordered pair A comma B belongs to F. For example, if A is a set containing the elements A, B, C and B is a set containing the elements 1, 2 and F is the function defined by the ordered pairs A, 1, B, 2 and C, 1, then F is just the rule which associates 1 with A, 2 with B and 1 with C. A point to note, there are two important points about the definition of function to be noted. First, every A in the set A must be the first coordinate of an ordered pair in the function. Second, each element of A must be the first coordinates of exactly one ordered pair. What is the image? When f is a function from A to B, the element B belonging to the set B, which is uniquely determined by the element A belonging to A, is denoted by f of A and is called the image of A. Thus, the ordered pair A comma B belongs to f if and only if B is equal to f of A. The notation of function. We use the notation f colon A to B to mean that f is a function from A to B, and by writing f from element A to element B to mean that f of A is equal to B. Thus, the function f is equal to the set of ordered pairs A comma 1, B comma 2, C comma 1 could also be illustrated by a function f from 1 to x, 2 to y, 3 to x. I am going to explain how a function is defined and how the various types of functions with the help of examples and some pictures that will also help you to understand it better. So, I am going to show you what a function is like. So, there are actually two structures. So, whenever we define a relation, it is between two different sets. So, this is the domain and this is the codomain. And a function f starts from the domain and maps an element to the codomain. We start here and we go to the codomain. The number of elements which are mapped onto these elements here. So, let us say there are 10 elements here and they are mapped onto 5 elements from here, say A1, A2, A3 etc. and there are B1, B2, B3, B4 and B5. Let us say that they are mapped by some arbitrary relations of some kind or the other. Now, the range is this entire set of elements. So, the range will be this mapping is actually giving me a mapping onto 5 elements. So, B3, B4 and B5. So, this is the range of this function. So, beyond this there are no other elements to which they are mapped. So, which means that this happens to be the range. So, we have seen domain, codomain and range. So, what is a function actually? So, this is where we need to remember that certain elements have to be mapped in a certain way only. For example, this is an example of a function. Say A1, A2, A3, A4 and A5, and these are all elements of a set A. The mapping is from A to B. So, the function is defined as from A to B, and these are the elements B1, B2, B3, B4, B5. Now, you can see that A4 and A5 are mapped onto B5 itself, whereas there is an element B3 which does not have any pre-image here. So, it is standing alone without any pair. The other elements are having proper pre-images. So, this when flowing, so B1 is an image of A1 and A1 is the pre-image of B1. So, image and pre-image is also the concept that we understand in functions. Now, this is an example of a function. Now, I will show what is not a function. Now you can see that there is one element A4 in my domain A which does not have an image in the codomain. This is not a function. One more example of something that is not a function is even if I have an image here, say B4, and imagine there is another B5, and let us say A4 is also mapped onto B5. This is also not a function because one element cannot be mapped to two different elements, whereas this is a function. So, all of these elements are being mapped to B only. This is an example of a function. Now, you might wonder what is the difference, because from A in the domain cannot be mapped to two different images, but all of them can be mapped to the same image. One way of remembering this is that one person cannot be in two places at the same time, whereas all of them can go to one place at a time. So, this is a way of remembering what can be a function and what is not a function. Now, we shall see something called 1-1 functions, onto functions, and 1-1 and onto functions. I hope you have understood what functions are. Now, we shall move on to the different types of functions. Now, as you can see, all of these terms have a mapping here, and there is a B3 which does not have a pre-image. Now, this is an example of a function which is not onto. Why is it not onto? Is because this particular element does not have a pre-image. So, in an onto function, all the elements on B have a pre-image in A. Now, is this an onto function? Yes, it is an onto function, because there is only one element in my codomain and that element has so many pre-images. It does not matter if it has a pre-image or not, it is onto. So, there should not be any element without a pair here. If that is so, then we say that it is not onto. Whereas, what is 1-1? 1-1 is they all have unique images. Now, this example is not 1-1. Why? Because all of them are mapped to the same element here. So, it is not 1-1. So, a 1-1 function will look like this. So, this element, yes, this should have an image. There could be other elements without any image, pre-images, but this is an example of 1-1, but not onto. So, as you can see, all of them have unique images, So, this is an example of 1-1. So, a 1-1 function is also called as injective, and an onto function is also called as surjective. Together, these two are called as bijective. So, a bijective function will have both 1-1 and onto function, right. So, we shall see some practical examples. So, these are merely set representations that I showed you to make you understand what 1-1, onto, range, domain, codomain, etc. are like. But let us see some practical examples now. Now, consider the function f from R to R by f of x is equal to 2x. Now, you can see that f of x, all the elements will be, whenever you take 1, it is mapped to 2. So, whenever you map 2, it goes to 4. So, every element is doubled. So, twice of every element is what is on the right hand side, in the codomain side. So, this is an example of a function which is 1-1, but not onto. Why? Because you can see that there is 1 here, 3 here, 5 here, and so on. All of these elements do not have a pre-image here, which means that it is 1-1. Do they all have unique images? Yes, they do. So, it is 1-1. But do all these elements in the codomain have a pre-image? No, they do not. So which means that it is an example of a 1-1 but not onto function. Let us see another example. Consider the function f from r to r by f of x is equal to x squared. So every element that you plug in, it is squaring and mapping that element. So which means that r, of course, although we are showing them as only integers here, you should remember that there will be numbers even in between the integers. So -2, infinity, so on, -2, -1, etc., 0, 1, 2. So as you can see, -2 squared is 4, so that is also mapped to 4. 2 squared is also mapped to 4. -1 will be mapped to 1. 1 is also mapped to 1 because 1 squared is 1, -1 squared is also 1. 0 obviously will be mapped to 0, so on and so forth. So 3 squared would be 9 and -3 squared would also be 9. So you can see all these terms are mapped. So there are 4 has actually 2 pre-images. It has 2 pre-images, namely 2 and -2. So is 4 1 1? No, it is not 1 1. 1 1 means there should be unique images only. So it is not 1 1. But is it onto? Could there be onto-ness in this? But no, because can you see 2 here, 3 here? They don't have any pre-image. So which means that there is no element here which will give you, the square of which will give you 2 or the square of which will give you 3. Hence 2 and 3 are standing alone without any pre-image, which means that this is an example of a function which is neither 1 1 nor onto. Now let us come to the next example, a function from the set of integers to integers given by f of x is equal to x. This is the best example of 1 1 and onto because all of these elements are mapped to they are themselves. So x is equal to x means whenever you plug in x, it is going to be mapped to x itself on the codomain side. So -1 is mapped onto -1, 0 is mapped onto 0, 1 is mapped onto 1. So 1 1 and onto. All the elements have a unique pre-image, all the elements have unique images, all the elements have pre-images. So it is 1 1 and onto, or in as per our definition, it is a bijective function. Now let us see one more example which is onto but not 1 1. So from z to the set of whole numbers given by f of x is equal to modulus x, which means that whenever you plug in a number, it is creating the positive version of that number only. So whenever I put in -2, it is mapped onto 2, -1 is mapped onto 1, 0 mapped onto 0, 1 is again mapped onto 1 and so on. So all the negative numbers are being mapped onto the positive versions of themselves. So which means that every element is going to have a pre-image but not 1 1. So there is no uniqueness. Can you see that these two have the same image here? So when two elements have the same images, naturally 1 1-ness is removed. So onto but not 1 1. I think these examples will suffice to help you understand what are the different types of functions, what are the elements of a function, the domain, the codomain, the range, etc. And the study of these functions is important, and it is imperative that you internalize these concepts so that you understand the subject better. In this session, we have studied about relations. We understood when a relation is said to be reflexive, symmetric and transitive. We also understood about equivalence relations, and also some examples in this context were discussed. Some key results associated to these topics were also covered in the main part of the session. We also studied a bit about functions, the different types of functions as well. I hope that this module was helpful in your understanding of the various concepts such as relations, equivalence relations, functions, the types of functions, etc. I hope it was useful to you. Thank you.